The next talk in the session is a characterization of graph properties testable for general planar graphs with one-sided arrow. And it's all about forbidden subgraphs. Artur will give the talk.
Yes, thank you. So I remember that when I was checking the title, I found that this is the longest title of the conference. I'm very proud of that. So first, I will just tell you very briefly what are the main results that we would like to present here. So the first main result is that testing H-freeness, so testing whether a given graph exists, a copy of a given graph exists in a planar graph, can be done in planar graphs, even for unbounded degree graphs. And this can be done in constant time with one-sided error. And then kind of will complement this result by showing that essentially all graph properties which are testable in constant time with one-sided error for planar graphs are exactly of this sort. So any property is essentially in some formal way just testing whether a given graph has a copy of, given planar graph has a copy of a graph H. Okay, so let me first kind of start with my vision of graph property testing. Our main goal here is to study graphs and check whether they have properties. So this is general goal, but our goal is kind of to study all possible graph properties and actually think about all possible graph representations. And there are many of them. So for example, the very first model of graph of property testing for graphs was developed by Goldratt, Goldwasser. They were considering a model where a graph is given as adjacency matrix, and we are saying, okay, we have some given graph property. For example, graph is 5 colorable. And we are saying we want to accept any graph which is 5 colorable, but want to reject graphs which are epsilon far from being colorable, which in that case means we can, so in order to get a graph which is 5 colorable, we have to modify at least epsilon fraction of input representation, means epsilon n square entries in this matrix. So this is a very natural model, has been studied for several years. Now we know almost everything. So that's quite impressive. So first of all, there have been some very nice results by Alon Goldratt and Trevisan, who showed that there is some special class of algorithms which will essentially, it's enough to consider only this class of algorithms. And then there came very strong results which are essentially showing that so we can characterize any property which can be tested in constant time with constant number of queries. And here constant always will be assuming that epsilon is a constant. Okay, so the next model was more natural model for many graph algorithms, which means our graph is given as kind of adjacency list. So in this case, the main interest in the case when the graph is bounded degree. So for every vertex, we can check, okay, give me all the neighbors of a given vertex. So this kind of more natural to some extent in algorithmic sense model. And we can kind of sample a random vertex, and then we can ask for a given neighbor, the 5th or the 10th neighbor of a given vertex, or learn that the degree is lower than that. And the model is very similar, kind of here we are assuming that graphs which are epsilon far from given property, we have to modify at least epsilon dn edges to obtain graph with property. And then this model is somehow understood. So I remember when 10 years ago people were talking about that, very little was known. Now we kind of understand something, but we still don't have good characterization. We know that, for example, testing H-freeness can be done in constant time. Testing bipartiteness, expansion, required root of n time, and can be done in root of n time. And I think last Fox or previous Fox, there were results showing that, for example, planarity can be tested with root of n queries for one-sided error and actually in constant time for two-sided error model. So these are the classical models. However, the point is that if the degrees are unbounded, if we don't make an assumption about the input graph, then these techniques just don't work. So the focus here is what can we do about general graphs, even if they're sparse, and the answer is we know very little. Okay? There are some results, but very, very few of them. So here, if we have general graphs, we have to carefully think about the model. And in this talk, I'll be just sticking to one model. So I can always sample a random vertex, and then I can ask for a random neighbor of that vertex. And then this is kind of a model where I have access to every edge somehow. One can also consider another very similar model, and I think it was originally proposed, that we can ask, okay, we query a vertex, we know the degree, and we are saying, okay, the degree is D, then give me a degree, any number between, give me a neighbor which has a number smaller than D. That's another model that people have been considering. So we want to study these graphs, this property testing in these graphs. And as I'm saying, almost nothing is really known. And kind of one reason is kind of this very natural example showing that this problem is kind of difficult for many problems. So think about the following setting. For example, you want to check whether a graph has a triangle. Okay? And suppose you have two problem instances. It's an empty graph on n nodes. Of course, this graph doesn't have a triangle. And then you have a clique of root of n nodes. The rest of the vertices are isolated. Then if all what you have to do is you are testing a random vertex, you need at least root of n time. So this is kind of causing some serious problems in designing any algorithms and analysis. And for example, this leaves trivial lower bound for testing h-freeness, planarity, and so on and so forth. So in this talk, we want to think, what can we do with this very short list of problems where we can solve anything, where we have some good information, feeling what problems can be solved, and want to focus on sparse graphs. And sparse graphs will be planar graphs. Now, several years ago, together with Moremizadeh, Onak, and Sohler, we showed the following result. So the problem of testing bipartitness in general planar graphs can be done with constant number of queries. Okay? So bipartitness is kind of very important problem in property testing for graphs. It's a benchmark problem. So all the models that I have presented before, kind of one of the very first problems studied was bipartitness. So we took this for planar graphs, and we showed, okay, for planar graphs, we can solve it. Then the question was, what else can we do beyond planar graphs? And in this talk, we'll try to extend this. So I will show you how to extend this result to testing h-freeness. Now, an interesting thing about a bipartitness paper is that one of the very first steps which was done in that paper was reduction really to problem of finding a cycle, just cycle of odd length. And if we know, okay, we know that every graph is bipartite if only if it doesn't have odd length cycle. So the first construction was graph is not bipartite, or is epsilon far in some setting, if only if we have odd length cycle of short lengths. And then we'll be looking for such cycles. So here our goal is take arbitrary graph H and check whether given our graph is H-free or not. So once again, this is our main result, the first result. And then we also have complementary results showing that to some extent testing H-freeness is all what we want to study here, what we're studying here. I'll be focusing on this result because this is really the most difficult, the most challenging part. I will very briefly mention about this model, this result here, at the end of the talk. Okay, so this is what the problem is about. So we are given some fixed graph H, for example, I don't know, a cycle with 25 vertices and some extra edges. And our input graph is a planar graph, and want to check whether G contains a copy of given graph H, or it's epsilon far from H. Epsilon far, once again, means we have to remove at least epsilon fraction of edges, so epsilon n edges in the case of planar graphs, to obtain a graph which doesn't have a copy, which has a copy, which doesn't have a copy. Okay, so here is really the algorithm that we're studying. So our algorithm is very simple. To some extent, it's doing the following thing. So you take a random vertex, run many times BFS-like exploration algorithm of constant lengths, of constant depths and constant breadth. What does it mean? Take a random vertex, and then run BFS. The problem with BFS is that in general, if the vertex has huge degree, it won't be running in constant time. So what we're doing is just take only a constant number of neighbors at random. And then from each of the leaves, take a constant number of neighbors at random. And do this only in constant depth of the BFS tree. Okay? So this is the whole algorithm. And now, the main result of this paper is really, if the input graph is planar, which is epsilon far from H free, then this algorithm with a constant positive probability will find a copy of H. Okay? It's obvious that if graph is H free, we won't find a copy. So this algorithm is always, so this is trivial part. The difficult part is that if the graph is epsilon far, that we'll be able to find a copy of graph H with constant probability. And as I was saying, and testing bipartitness was very similar. The algorithm was essentially doing this in a simpler way because it was not doing anything like BFS search. It was just doing a random walk. So because all what we wanted to do for bipartitness was to find whether it's CK free for odd K, we were just looking for random walks, and if one of them found odd length cycle, we're done. So now our goal was to extend this, and this is kind of a natural extension, but the main problem here, and this took us a lot of time to study, is that before we were looking at cycles and passes, and the analysis was very complex. Now we have something more complex. We have BFS-like trees. And the analysis took us more time, but we finally got it. So this is exactly what I was saying. Constant random walks. So you should think, what do we know about random walks of constant length? Usually we know very little. We know that if you have an expander, you are running logarithmic length random walk, you reach a random vertex. But this is a constant random walk. It's constant length random walk. So it's more difficult to say anything. So here our goal was to do this actually for BFS-like exploration. And once again, it is really enough to focus only on one run of this algorithm. So what we wanted to show is that a single BFS-like exploration algorithm, starting at a random vertex with a constant positive probability, will find a copy of H if the input graph is epsilon far from H free. And we'll have kind of two central claims. The first one is trivial, very easy at least. And the second one is kind of more difficult and requires lots of work. So let me start with the first one. The first one is saying that if a graph is H epsilon far from H free, then this graph will have lots of copies, disjoint copies, edge disjoint copies of graph H. Okay? So this is kind of our starting graph. So we have graph G, and then we are saying it will have lots of copies. We don't have to find them. The algorithm will have to find them at the end, but kind of this is an existential claim. And that's easy to show, actually. The second claim is that we do have some special construction of a subgraph of graph G, which will have the following two properties. The first one is saying that if we run our graph exploration, BFS-like exploration algorithm on the original graph, and the algorithm will find something, then on this new graph G prime, which is a subgraph of G, will find with constant times the original probability. The probability will be lower, but it will be lower by constant. And then the second thing is that the tester, this BFS exploration algorithm, will find a copy of H with constant probability in this graph G prime, G star. And kind of about the first step, so we will construct the graph G star, and what really we want to have are two very important properties which will ensure that the first property is satisfied. And these are the following properties. So first of all, G star must have a constant fraction of non-isolated vertices. And then for every non-isolated vertex, its degree just decreased by a constant factor, not more. Now, why do we need that? So what is our algorithm doing? The first step of our algorithm is take a random vertex, and then the random BFS, this bounded depth BFS. So if we start a random exploration in G star, by the first property, we know that we have constant probability that we'll hit one of the vertices that the original random walk, the original algorithm for graph G would be looking at. And the second thing is that if we are following any path in graph G, then with constant probability, this path also will be in graph G star. Okay? We have these two properties, and with them we can reduce this fact that it is really enough If we have these two properties, it's enough to show that a graph G star, if we can find in it copy of H, then we solve the problem. And now how to generate this graph G star. And this is kind of quite complex, so I will just give you some very brief overview. We'll start with a collection of edge disjoint copies of H. This is what we know what we have at the beginning. And then we'll try to shrink them. And we'll be shrinking them in the following way. We'll be using the following construction. So suppose that this is my graph H. And then the observation is that that I can ignore these vertices, in this case 1 and 5, if I know that whenever I will hit any of vertices 1 or 5, then I will actually be able, with constant probability, explore all neighbors of vertices 1 and 5. And with this, to some extent, I can remove this vertex from my construction. I can contract the graph. And here's kind of maybe another description. So I'm saying I'm shrinking graph H so that if normally I would hit one of these vertices here, then I will be able to hit all of them which are in this gray area. Once I have this, I will try to model this using hypergraphs. So what I'm trying to do, so this kind of sequence of reduction for my copy of H, and then you should think my original graph, I already reduce it somehow, and I have only lots of copies of H, and I have to find one such copy. So what I'm doing is, I'm doing this reduction as I had before, so I contract this piece, I contract this piece, I contract this piece, and these are hyperedges. What will happen at the end, that I run a sequence of contractions, so that at the very end, I will have a very simple graph. And the claim is, this will hypergraph, and this hypergraph I will be able easily to check whether the copy of something which originally was graph H is now in the shrunk copy of the graph. So this is really the procedure that I just described here. Analysis of this is quite complex, but kind of this is really the sketch of the approach. And the key part is that because at the end, the graph H is represented by a single hyperedge, I can easily check whether my shrunk copy of graph G has a copy of H or not. This is kind of very technical because we have to use the fact that the graph is planar. And as you might know, it's kind of difficult to say what does it mean hypergraph is planar or not. We don't really understand planar hypergraph well. Then we're using some tricks, for example, with coloring vertices. So these are lots of technicalities which, please, you're welcome to study in the paper. And with this approach, we're able to prove our main result, so that if we are given a planar graph, we are given graph H of constant size, we can check whether the graph contains H or it's epsilon far from H with a constant number of queries, and this algorithm has one-sided error. And as I said, we also have full characterization, which works only for the model. I mean, at the beginning, I was focusing on some models, and one of the models was that for every vertex, we can ask for a random vertex and then random neighbor. So in this model, we have full characterization, which follows from the fact that essentially we have canonical algorithms. We can argue that any constant time algorithm must have some special form. And for these algorithms, we are showing that with one-sided error, all what these algorithms can really detect are copies of some subgraphs. And with this, we have this characterization. Okay? And then furthermore, one can extend this beyond planar graphs. We can have graphs with arbitrary fixed forbidden minors, etc. Okay? Thank you very much.
We have time for questions.
Yes, Yuri.
Can you say briefly what does planarity have to do with it, or how does it help in testing?
Planarity is essential for contractions. So to some extent, so in the proof we are really, and we had to work hard to ensure that we are using it in the right way. So for cycles, for example, so for bipartiteness, what we're showing that we know that every graph has degree at most 5, so then at least one vertex of degree at most 5. And then with that, we're able to show that if there is a cycle, that there will be some cycle which will have low degree vertices. And then we can remove the lots of edges. But for that, we need, if we want to argue that we are removing only constant fraction of edges, we need to have low degree. So this kind of property of planarity. I remember that some time ago, some of my colleagues was asking whether one can go much far beyond planarity, for example, for constant aboricity. I have no clue how to do anything like that. We do use the fact that we are contracting graphs. Any more questions?